I'm going to walk through the 1.4 to 3.5 quiz review worksheet. So number one, we have the piecewise function given here, and we're asked to find these various limits. So for part A, limit as x approaches -4 from the left side of -4 of g of x equals, and we have to determine, since this is a piecewise function, which branch this graph is referring to. So -4 from the left side of -4, so that's going to be less than -4. So that's going to have to be this branch right here. So if we want to find the limit as x approaches -4 for this branch, then we're going to first identify this function, and then we go through our appropriate steps. The steps that we take is we always try plugging in, and when we plug in, we're going to get 9 minus 16, which is -7, all over 0. So, or 16 minus 16, which is 0. 4 squared minus 16 is 0. So we get -7 over 0, and that indicates that there's not going to be any common factors to reduce. This would be a limit does not exist. However, we see that there is a one-sided limit indication here. So we have to determine, because there is an asymptote here, we have to determine whether this is going to be approaching positive or negative infinity. And so this is where we have to choose between those two options by plugging in a decimal value that is close to -4 from the correct side of -4, and then determining the signs. So here we can choose -4.1. So 9 minus -4.1 squared. This will give me a value that is larger than 9. So 9 minus a value larger than 9 will give us a negative value. And the denominator will be -4.1 minus 4. -4.1 minus 4 is -0.1. -0.1 squared will be positive. So negative over a positive will be negative. So we know that's going to be negative infinity. Okay, part B, limit as x approaches negative infinity. So if we're approaching negative infinity, then we're simply looking at the degrees of our function. So if we look at our degrees, well, first off, negative infinity is referring to values less than -4. So we're talking about this piecewise here. So if we look at this piecewise here, we have, if we're just comparing between degrees, we see that negative x squared over x squared will simply give us -1, because degrees are the same. So we simply take the leading coefficients. -1 over +1 is -1. Limit as x approaches -4 from the right side of -4. So this is referring to this portion of the graph. So if we plug -4 in, we get -4 squared over -4 plus 2. So -16 over -2, which is +8. Notice the difference between A and C. With A, because we got a limit that did not exist, we have to go take that extra step further evaluating this one-side limit. However, with this one, when we plugged -4 in, we got a real number, so we don't have to worry about any additional step with the one-side limit, because we already got a real number. We already got a solution, so there's no need for us to do any more work. Okay, so again, with the one-side limits, you're only going to treat this differently if you get a does not exist, and you're forced to have to choose between positive or negative infinity. Okay, part D, limit as x approaches -4. So this is simply saying that in order for a limit to exist, that means the two branches approaching -4 from either side of -4 must equal the same value. So we already found the two one-sided limits, right? From the left side of -4, it's going to negative infinity. From the right side of -4, it's going to +8. Obviously, these are not the same values, so we can say that the limit does not exist because the one-sided limits do not agree. Okay, limit as x approaches positive infinity. So let's identify the appropriate piecewise function. positive infinity is greater than negative 4, so it's this portion here. So negative x, so when we're evaluating positive infinity, we can simply look at the degree. So degree is higher in the numerator than denominator. So all we need to do is to determine whether it's going to positive or negative infinity, because it has to be one of those two options, because x squared is going to increase at a faster rate than the x. So if we plug in the large positive value, we're going to get still going to get a negative over a positive, which means that this graph will go down to negative infinity. Okay, step through continuity conditions for number 1 for the piecewise function above. Then state the reason for discontinuity. Identify the type of discontinuity. So the first condition is simply the ordered pair. So ordered pair, f of negative 4 is 2 minus negative 4, which is positive 6. So we see that the ordered pair exists. Condition 1 passes. Second condition is saying that the limit exists. And we already saw from part D from number 1 that the limit does not exist because the one-side limits do not agree. So second condition fails, and because second condition fails, we can say that this is going to be a non-removable discontinuity since the limit does not exist. Okay, number 2, find the horizontal asymptote for f of x equals negative x minus 5 over square root of x 4x squared plus 12x minus 30. And horizontal asymptote is same thing as finding limit as x approaches infinity. But in this case, with this special case of the radical in the denominator, we have to consider both limit as x approaches positive infinity and at negative infinity, because we may have two different horizontal asymptotes depending on whether we're following the left branch or the right branch. So with positive infinity, we're just going to divide by the variable of the highest order. In this case, it is x, but the denominator is going to be under the square root, so we have to put x squared there. So divide every term by x and the denominator by x squared once we have it under the square root. So that's going to give us negative 1 minus 0 over root 4 plus 0 minus 0, and root 4 reduces to be 2, so negative 1/2. Okay, for negative infinity, we do the same thing. We just have to account for the fact that it's approaching negative infinity, so we have to include an additional negative outside our expression. So then that's going to still give us negative 1 over root 4, but then there's an additional negative, so that's going to give us a positive 1/2. Number 3, show whether Ivt applies. So with Ivt, we have to first show that our function between our intervals is continuous, and after that we have to plug in our endpoints to determine what the y values are, because we need the y values to sit above and below this k value of 2. So whatever y value we get, one needs to be above 2 and the other needs to be below 2, so we can guarantee that the graph is going to cross the y value of 2 at some point between the endpoints. Okay, so first, we see that there's a vertical asymptote at x equals 3, and so it's possible that the function may not be continuous within our interval. However, 3 is sitting outside the interval of our endpoints, 4 through 8. So we can say that our function is continuous on the interval 4 through 8 because even though there is a break in the graph, that break is not affecting our interval. Okay, so it passes the first condition. The second condition is having to test the endpoints. So let's plug the endpoints in. Plug in 4, we get 4 over 4 minus 3, which is 4. Plug in 8. 8 over 8 minus 3 is 8/5, and 8/5 is about 1.6. So let's compare these two y values. Between y value of 4, y value 1.6, now our target y value is 2, and 2 is sitting between 1.6 and 4, so we know that Ivt will apply. The graph is guaranteed to cross the y value of 2 simply by knowing that our graph is continuous and our endpoints sit above and below our target y value of 2. Okay, so now we've shown that Ivt applies. The graph will cross y value 2. Now we need to find c. So we need to find the location, basically the x value, where equals to 2 occurs. So we basically want to find out when is the graph going to cross the y value of 2. So we just simply set these two equal to each other and solve for x. So x minus 3 is equal to 2. We want to find out when the graph crosses a y value of 2. We do cross product, and 2x minus 6 equals x. Solve for x, x equals 6. So c is equal to 6. Now 6 is between the x intervals of 4 and 8, so that checks out. So we know c is equal to 6. Hey, oh, and the sentence that we can write out, since our y value sits between the endpoints y values, Ivt applies, and c exists in the interval. Okay, finally, we're looking at the graph to determine the values. Okay, so limit as x approaches -5 from the left side of -5. So if we approach -5, okay, from the left side of -5, that means we're talking about this branch. As we get closer to -5, we see that y value is going to positive infinity. Okay, limit as x approaches -infinity, so we're going to follow the graph to the left. So if we follow the left branch, that's going to be this portion here, and this graph is approaching a y value of 3, so that's our limit. Approaching 4 from the right side of 4, so here's 4, we're going to follow the right branch, so this branch will lead us to the y value of -2. So remember, one side limits will still exist even if the endpoints do not exist. So as long as whatever that branch is leading towards, that will basically tell you what that one side limit value is. Limit as x approaches 7. So in order for a limit to exist, this is no longer one-sided. We need both branches of the graph to arrive at the same y value. So here's 7. Okay, as we approach 7 from both sides, we see that the graph connects to the same y value, and that y value is 4. Okay, finally, limit as x approaches positive infinity. So we're going to follow the right branch. So the right branch heading towards positive infinity is going to be this portion here. So this portion we see is leveling out at the y value of -4. So -4 is our limit as x approaches positive infinity.